Hi guys, today we will discuss about the implementation of my mini calculator. The description for this project was to create a mini calculator that can perform addition, subtraction, and multiplication of two 4 bits input. For my project, I had 6 parts. The circuitry was divided into 6 parts. The first part was the display input A and B. The second part was the other subtractor circuitry. The third part was the other subtractor display. The fourth part was the multiplication circuitry. The fifth part was the multiplication display. And the sixth part was the output switcher between the other subtractor and the multiplication display. We will discuss them quickly in this video. So for our input, we simply need to display the input of our 4-bit input A and 4-bit input B towards a 7-segment display. So we have created a truth table for the ones digit. This is the ones part of our circuitry, and this is the truth table. And with that, we have created K-maps for A, B, C, D, E, F, and G. So for the input A ones, we name the output as input A ones because it means that it's the ones digit of the input A. So as you can see, the outputs of all of these Boolean expressions were connected to a 7-segment display in the ones digit of the input. And for the tens digit of input A, a separate truth table was created. So this was the truth table for the tens digit. And as we can see, this was the resulting Boolean expression for the tens digit, which is A and B plus C, and it was connected to the tens of the input A. So for our input B, which is in this part, as you can see, let's expand the circuitry. Input A is the exact copy of input B. The only difference is that input A had A3 and A2, A1, A0 as input, and input B had B3 to 0 as our input. So they are basically the same, input A and input B. When you display, example, when you put 1111 in input A and 1011 in input B, we can see that input A has a 15 of value and input B has an 11 value. That's it for the first part of our logic circuitry. The second part is the other subtractor circuit. So in this circuit, we need to be able to add and subtract the 4-bit input A with the 4-bit input B. So of course, we will look at our other subtractor circuit. This is our other subtractor circuit in which we have inputs A and B. A, B, A, B, A, B, A, B. And we have, this is our sub. This will serve as the indicator whether we need to complement B so that a subtraction will be created. And of course, we have inputs C4, S3, S2, S1, and S0. However, we need to take note that if the sub is equals to 1, we need to neglect our C4. And this serves as our neglector circuit. The neglector circuit, as you can see, this can neglect C4 if the function is subtraction. So, with given that, our new outputs are S4, S3, S2, S1, and S0. Now, we have the other subtractor display, or the BCD add sub to 7 segment. This is the circuit for the BCD add sub to 7 segment. It's kinda long. Okay, let's look at them quickly one by one. This is the truth table for the 5-bit input from S4 to S0. So we have 000 up to 0 to 31, and these are the respective outputs for our 7 segment. Again, this is divided into tens and ones. So for our ones digits, this is the segment A for the ones, segment B for the ones, segment C for the ones, segment D for the ones digit, segment E for the ones, segment F for the ones, and segment G for the ones. For the tens, we have these 4 Boolean expressions. So all of the expressions are in the written report. If you want to see, you can see the different expressions in there. So I have also created a truth table for the tens 5-bit segment to the tens digit. Again, these were then connected to our display. So now we are finished with our third part, which is the other subtractor display. And we will proceed to the fourth part, which is the multiplication circuit. The multiplication circuitry consists of many different full adders and half adders that are cascaded with each other. As you can see, we will zoom in here to our multiplication circuitry. We have inputs B0, B1, B2, and B3, and they are connected to inputs A3, A2, A1, and A0 through half adders and full adders. So this is the circuitry. So as the output, we have P0, P1, P2, P3, P4, P5, P6, and P7. So these 8 bits, they will serve as our input to our 7-segment display. But before that, we first need to transform this 8-bit circuit to the BCD ones, hundreds, and tens. So to do that circuitry, we need to move on to our 8th product to BCD converter. So this is one of the longest circuitry in this project. As you can see, the 8-bit product to BCD. So this circuitry involves decoding the 8 bits product P0 to P7, as you can see, P7, P6, P5 into different BCD, which are called ones 0, ones 1, ones 2, ones 3. So this will serve as the 4-bit BCD for our ones digit in the segment, and this will serve tens 0, tens 1, tens 2, tens 3. This will serve as the 4-segment display, 4 bits for our 7-segment display in the tens digit, and the hundreds digit for the last. So these were created through different gates. So afterwards that you have now this ones 0, ones 1, ones 2, ones 3, tens 0, tens 3, and hundreds 0 and hundreds 1, we now have 2 outputs, and those outputs should be routed to our 7-segment display. As you can see, this is the circuitry. This is the multiplication output to the 7-segment. So this is the 4-bit for our ones, and the 4-bit for our tens, and the 2 bits for our hundreds. This is the truth table for the ones, and with the corresponding Boolean expressions. This is the truth table for the tens. For the tens, it's basically the same as the ones, only the input is changed. For the hundreds, we have a truth table with 2 inputs only and Boolean expressions. So, with that in mind, we are now heading to our last part of our circuitry, which is the output switching between other subtractor display and multiplication display. We should take note that earlier, we created 2 separate outputs, which is the output for the multiplication and the output for our addition or subtraction. So to switch operations, we have created the circuit. So if subtract is equals to 1, then the whole circuit will subtract. If add is equals to 1, the whole circuit will add. And if multiplication is equals to 1, the whole circuit will multiply. So multiplication was created as an enable so that it will override the output for the addition and subtraction if ever it is necessary. So we created this simple enabler from the multiply, which is if multiply is equals to 1, as you can see here, if multiply or multiplication is equals to 1, the circuit will follow the output of the hundreds. The circuit will follow the output of the multiplication display. However, if multiply is equals to 0, the circuit will follow the output of the addition and subtraction display. So let us try. Okay, let's turn on add first. It's loading. So we have an input of 15 and 11. So since we turn on add, the output should be 26. Yes, the output is now 26. So if we turn on subtract, the output should be 4. And now the output is 4. But we turn on multiply, as we said earlier, if multiply is on, the display should be the multiplication product. So if multiplication is on, we have 15 times 11, and 15 times 11 is equals to 165. So let's try other values first. So to confirm the effectivity of the circuit, we have 14 and 10. So 14 times 10 is equals to 140. And let's try to add 14 plus 10 is equals to 24. And 14 minus 10 is equals to 4. So to zoom out the overall circuitry so that we can see the different parts, this is the overall circuitry of my project. We have input A, input B, adder subtractor, multiplication to BCD 7 segment, BCD add sub to 7 segment in this part, and the 8-bit product to BCD in this part, and the multiplication circuitry. So that would be all for my video report. Thank you.